Okay, everybody, I think it's about time to get started. So first of all, let me remind you again, using audience mics, so, keep your commentary.
You're not using one.
Sorry?
You're not using one.
I'm using the audience mic because I'm projecting my voice into the audience mic. So don't mumble questions and stuff like that. So, and Yolanda Gill is our speaker today, so we really all know Yolanda, so what I should have done is research something that everyone didn't know, but I didn't find any answers, so sorry about that. But what I can tell you is this. So the reason we're getting this cool talk today is that Yolanda was invited to give a keynote at the International Semantic Web Conference. So we're getting sort of a preview of this talk. So thanks a lot.
Thank you. Okay, so I've worked for many years. My research has focused on representing and reasoning about tasks. And I think it's a very important research area, and I don't think there's enough talent invested in it. So I'm hoping that with this talk I'll convince you that it's an important topic and maybe sway some of you to work on it. I titled the talk Semantic Challenges in Getting Work Done. So all of us do a lot of work every day, so I hope you'll identify with some pieces of the talk. I thought about calling it something like Confessions of a Workaholic. I've always been very focused on work and getting stuff done. It's kind of an obsession of mine. Then I thought it would be Confessions of a Semantic Workaholic, which is much more appropriate. I always want to represent tasks and reason about them. I've always been this kind of very focused on work. I came to the US from Spain because I could not stand how many obstacles there were to getting work done. So every day I think very hard about how to be more efficient. I think things have changed a lot in Spain since, but anyway. So I want to talk about something personal that involves all of you, which is managing your to-dos, some work that we've done there. So every day you get a lot of work done and you track it. So I'm going to talk about managing to-dos. And then I'm going to talk more about science-type tasks. I'm going to talk about semantic workflows and ways to manage knowledge-rich tasks in science. And then I'm going to focus a lot of the talk on collaboration in science. How do you manage tasks when they're collaborative? Because that's the nature of most of the tasks that you really want to track and take a lot of our time. Okay? Along the way, I'm going to pose some semantic challenges in getting those kinds of areas to be successful. Okay, so I'm going to start with to-dos. So all of us keep track of a lot of to-dos. This is some of the examples of how I do it. I put a lot of to-dos on my desk. Those are kind of more daily, weekly things. I keep a lot of flagged emails. I'm sure you all get a lot of emails all the time. I have various forms of to-dos and tracking and so on and so forth. It's really crazy. So to-do lists are very, very used by many people, used more than calendars and contact lists, according to studies. There's many online to-do managers. I use some of them. I'm sure you also use some of them. And prior research has really focused on studying how people use their to-do lists, but not so much on helping them get things done. So this is a major opportunity. And it can have a lot of impact on all of us. So how do you get work done through your to-dos? So the to-dos involve lots of little things. For example, things at work: get an abstract for a talk, reserve a conference room, buy bread on the way home, find a hotel with a gym for someone who's visiting, and so on and so forth. And a lot of to-dos are following up and following up and following up with others, which I'll talk about in a minute. So there's a lot of opportunities to do interpretation of these to-do lists and to assist people with their to-do list. So for example, you can use software agents to help you accomplish some of these tasks. You can help people organize and group these entries. You can track the timing that you need to do the tasks ahead of time. You can maybe you don't know how to do some of these things. How do I reserve a room if I'm new here so I can get help from others and so on. So there's a lot of opportunities to help all of us more with our to-dos, and very little work has been done in any of this. So one of the things that we did when we started this work is actually study to-dos. So these are some examples. We just, for privacy reasons, no to-do company would give us to-dos from their users, so we just created our own to-do app. And we put it out there, and we gathered a lot of to-do lists from people. Very interesting because there are things like be a true Christian, updating the Mafia blog. A lot of things had to do with weapons. We were kind of concerned about this, but they were actually weapons for games. So a lot of things that involve, kind of wacky stuff. But many of them we could not really automate. I don't know if you can automate making somebody a good Christian. That's a challenge for you. But many we could automate fully or in part. Certainly things that involve buying or things of the sort. We also instrumented in an office environment people actually doing their work and jotting down to-do lists. And here we learn a lot about this. I won't spend a lot of time, but a lot of them could be automated by agents. A lot of them were missing a lot of details. What I mean by missing arguments, I mean they were missing who the person was. When you say Frank, there's 10 Franks, or, talk to Joe, but about what, or finish the report, which report, and so on. Only some of them, 33%, included a verb, so it's not clear when you put a person or an object, what are you supposed to do with it. So the way that we jot to-dos is very dependent on our context, our personal context, and that's not always captured. So it's very challenging. So we worked on managing to-do lists and helping you be more efficient with to-do lists through 3 approaches. One is using software agents that can make reservations or schedule meetings and so on. A second is to get help from colleagues. And the third one is to use online resources that tell you how to get things done, like getting a driver's license and things like that. So I'll tell you briefly about this. So using software agents, we describe the capabilities of these agents with semantics. We help map to-do lists to the capabilities of the agents. So, for example, the calendar agent would have a scheduled meeting with a person for a topic, time, and location. So those were the arguments of the agent. And so the to-do might be missing some of these things. You could fill them up with defaults, or use the context of the user to figure out what values should be there. And we actually had user interfaces that people could use and test this. Some of the things that we found is that we could have pretty high accuracy in detecting agents that would be relevant to your to-dos, but you still had to confirm that and actually provide enough details to the agent to get the task done. But this kind of work is interesting because we all schedule meetings by hand and do a lot of things by hand that maybe we can get agents to help us with. One thing that we realized very quickly is that having knowledge about tasks is very, very helpful. So we did a project called Verbocean where we were actually extracting from the web what is the right order between tasks and what's the duration of tasks. And this particular project focused on verbs. So, for example, we knew that before you delay something, before you delay a meeting, you have to schedule it. We also knew that lunch usually takes about an hour, and meetings or presentations take about 30 minutes on average. So that gives you also an idea of how to organize and track to-dos. Another project that we did is collecting knowledge about what is involved in doing a task. So if you say, I'm going to give a talk, what is generally involved, what are the objects that you need, and what happens if you run into any problems in the process. So trying to get more of a detailed of what a to-do might entail in detail. So that was one of the things that we explored. We also looked at managing to-dos by exploiting online resources. So we would go to online sites that, like WikiHow, for example, where they have recipes for getting things done. They normally follow a lot of steps, so we would let you mix and match steps and select the ones that suited your problem. But you could navigate through these chunks of processes and tasks very easily. Another thing that we do is collaborative problem solving. So I have something that I need to get done. Can I post that to do to my friends in a social network? They can tell me, oh, I can take care of this part of it. Say that you're organizing a party or writing a paper. And then people would sign up to different pieces and share their to-dos and help getting them done. We also had a way to publish how I got it to do done. So how did I get my driver's license? I did all the following things, and I went to this website and I did all this stuff. You could publish that, other people could reuse it. And what you see in the picture at the top is what we call a social task network. So how are people related through the tasks that they share, and how are they related to the task and to resources on the web. So it's interesting to see that tasks actually create an additional layer of communication between people in this network. So I'm introducing all these different pieces of work very quickly, but you can see that I would really love to have something that manages my to-do list and actually helps me get things done, whether collaborating with other people, whether finding agents that can automate things for me, or maybe other people that can automate things for me, and getting out on the web and getting me information. So I think this is a fantastic area of research. Some of the difficulty that we had was actually being able to measure the utility of the information, the actions that the system was taking, getting context from users. It's a really, really huge and challenging problem. So there's a lot of research that remains to be done. So I'm coming to the first two semantic challenges that I want to share with you. So one is all the semantics needed to manage personal to-dos. So first, you have to understand how they're expressed in natural language, how they correspond to tasks that we would know what they are. When you put a to-do, what other things do they entail? How do you prioritize the items and so on? The user interaction has a lot to do with, I jot a bunch of things. Is the system going to reorganize everything so that I don't recognize my to-dos, and helping me monitor them, prioritize them, and so on. But also a lot of knowledge about what's involved in doing a task, when am I going to be late if I don't get to it at some point? How do I order things optimally? How do I group things together so that I can deal with things that have a theme to them, and so on? So this is a big semantic challenge. And another one is just coordinating to-dos of different people. So the to-dos that take me the most time are the ones that take coordination. Who should I get involved? How should we get this done? Who should do what? And that takes a lot of effort. And so coordinating my to-do list with other people's to-do lists. I would like to know when they're late, when are they going to get things done, what do I need to do to help them, and so on and so forth. So that's a second challenge. Okay, so I mentioned that managing to-dos is really hard. Here's some readings if you're interested in this area. Managing to-dos is really hard. You're missing a lot of context and a lot of information about what the user wants. We're missing common sense knowledge. So I'm pursuing this kind of research in the context of science. So I'm going to tell you more about knowledge-rich tasks in science, how we use semantic information in science tasks, and then I'm going to talk about collaboration in science and the work that we're doing there. Okay, so when you think about science and the challenges that scientists face, you hear about big data, you hear about the amount of data that scientists have to deal with. We all know that. But I'd like to contend that the problem is really not the data. The problem is that there's a human bottleneck on how we process the data. So we do a lot of the science data processing by hand. So this is an example of the kinds of tasks that a scientist will do. What is the state of the art? What's a good problem to work on? What's a good experiment to design? What data should I collect? How should I analyze the data that I collect? What are the implications from those experiments? How do I revise my models? All of these things we do by hand, all of it. And I think that we need to help machines understand these processes, capture the semantics of these processes, these activities more, and that can be a game changer for science. So here's an example of a system that does this. This is Analyzer. It's work by Larry Hunter. And what it's doing is it's reading text from the biomedical literature, integrating what it's extracting with existing biomedical databases, and creating relationships between these biological entities. And based on these relationships, it's making hypotheses about what additional relations could exist and proposing those to the scientist. So the scientist doesn't have to read all those papers or find them in the first place and do the integration of all of this information by hand, which is what most scientists do every day today. So this is wonderful to help with the process of finding what's the state of the art, what's a good problem to work on. My particular research focuses on what is the best way to analyze data. So suppose that you've collected a lot of data from experiments, what's the best way and the most efficient way to analyze it? So I've been working on automating that process through semantic workflows, and let me introduce you to that idea. So this is an example of a science task that is very time consuming. So these are researchers that put sensors in the river, the Merced River, and have to keep track of what they're sensing over many months. They integrate that data with weather data and other information from web sources that are available to them, and they create all of these steps to process the data, and they do those steps manually. The interesting thing is that automating one step after the other is not a big deal. What's interesting is that some of the steps, they actually need to make an intelligent decision about them. So in this case, there's 3 different models to compute reaeration, which is how much air gets mixed with water. And depending on what's happening that day, they want to choose one model or another. So we build semantic workflows that actually capture this knowledge. So on the left is the workflow that I just showed you with that big round circle showing the 3 models. A semantic workflow is on the right. It's basically capturing what data goes to what steps, what software, and you can see in the middle that we actually have a step that says run reaeration model, and we'll make an intelligent decision based on the data of the day. The input to this workflow is daily data from sensors. You can give it data for many days, but it has a lot of semantic properties about the site and the average depth of the water and so on, which we're going to use, or the system's going to use to choose one model or another. So these semantic workflows actually can reason and make intelligent decisions and automate this task. So we have implemented and developed an environment to represent and reason about semantic workflows. This environment is called WINGS. You see a workflow diagram, basically the data flow diagram on the bottom right, and you can actually attach semantic constraints to any entities described in that workflow, so whether the data sets or the steps in the workflow. And we've developed workflow reasoners that propagate and use those constraints. All of that is built on semantic web standards, and we can run the workflows on scalable execution engines. So for a particular model, in this case the reaeration models on the left, I'm showing you just a hierarchical taxonomy of the types of models and what they accomplish based on the kind of data that they process. We also represent constraints on the data. So for example, a particular model processes raw sensor data, and we also put model constraints. So for example, the fact that the average depth has to be 0.61 in order for a certain model to be applicable. So we use all of those constraints to decide on what model to use. We also use those constraints to propagate metadata. So the input data set may have particular values for the location of the sensor and other things. So we'll propagate that metadata as appropriate through the workflow. So in the example that I was showing you for the daily data, I think you can see in this graph that at the beginning we're picking one model. As we get through the middle, over time the system's picking a different model, and then on the right when the flow is low again, it's picking a different model. So it's going to change the model and make an intelligent decision about what models to use. How do we do this? For us, the workflow is a plan. We use skeletal planning techniques to propagate these constraints in the workflow structure. And we've developed algorithms that basically do goal regression. They propagate the constraints from the goal, from the end state to the starting point, the starting data, and then a forward projection that propagates the constraints from starting to end. So if you have a constraint in the middle, in this case, this is an ensemble classifier, one of the algorithms for classification has a constraint that the input data has to be discrete. We'll propagate the constraints, and so we'll know that the input data at the beginning of the workflow has to be discrete. None of the other intermediate steps will change that property. So we use those algorithms. There's been a lot of work on composing web services, using semantics to represent processes and workflows, and web services as well. A lot of this work looks at assembling the workflow from scratch. So you have a problem, and it's composing the workflow. We found in our work that it's more reasonable to start with an entire sketch of the workflow. Scientists don't want you to put unexpected things in the middle, so they want a sketch of the workflow to start with, and then you can elaborate it. So we have developed algorithms to do this kind of many-stage workflow elaboration. So all of this is fueled by semantics. We have the algorithms and the infrastructure to do this. Scientists are getting very excited about this, so we just got a new project called GeoSoft, where we have scientists actually describing their models and their software with quite a bit of detail. So I'll show you, we're building on work on the community surface dynamics modeling system, where they've actually cataloged every variable in the environment that hundreds and hundreds of geosciences models work with. And based on those names, they've actually separated the objects that they talk about, the quantities that they're being measured, and then the operators, whether you're measuring increases or anomalies or different kinds of things. So based on this information, we can actually describe models and say, well, this one is using a land surface measurement, and it's the albedo, for example, if you're measuring snow. And we're giving you choices based on what properties apply to what objects, because there's a whole ontology behind this system helping with that. So we're very excited that the scientists themselves are getting interested in describing semantically and very precisely what their software does. I wanted to mention that there's a lot of workflow systems actually. None of them really use much in terms of semantics, so they simply represent the data flow, and they focus on other research topics such as sharing the workflows in repositories and populating the workflow system with components or models in a particular domain. So for example, some of you know the Loney pipeline. It has a lot of image processing components or gene pattern for genomics. So why are semantic workflows better than a regular workflow? So one of them is that it can actually automatically elaborate your workflow. So I showed you these algorithms that take a workflow like the one on the left, and it will say, well, you can use any algorithm to train topics, and maybe we have 3 different implementations. In this case, one is parallel, one is online, one is the regular LDA. And if you look at the algorithms, the papers of those algorithms, all of them say they're super fast, they're super good. So you can actually represent for what kinds of data or what kinds of problems the algorithm is better. And so Wings will help you generate a workflow with the algorithm that's best for your data. Another great thing about semantic workflows is that we can actually give access to data analysis expertise. So I like to show this graphic. It's from Science, so the Reviewers of Science, which is a premier publication of the AAAS. The Reviewers of Science were given a survey and asked if they have the necessary expertise to analyze the data they have. Now, these are the you could argue, the best scientists in the world that are reviewers of this publication. But they actually, the majority said that no, they don't have the skills that they need. They need to work with others. They need to find the skills to analyze the data elsewhere. So it's very important that if a lab has data analytics expertise with some particular type of data, that expertise is shared. So I'll show you how workflows capture this. If you want to, for example, classify a bunch of documents, so you have newspaper articles and you want to separate, classify and separate political news from sports news and so on, a very naive approach is to just say, well, I'll take the documents, I'll build a modeler, I'll run an SVM or something else, and then I'll classify my test data. And I can tell you this naive approach is used by professionals many times. I've seen it. The expert approach in this case would be, well, you take the documents, you do some feature selection, you compute a statistical correlation scoring, and then you filter the features so that you have less of them, and then you do your modeling and your classifier. So capturing this kind of expertise that's really not in the books. The books will describe to you different ways to do modeling, but they won't describe to you how these other steps are done. So we have found that actually preparing data and the expertise that is required in getting the data ready to actually run an algorithm that matters, like a classifier, it takes about 60 to 80% of scientists' time. And this is actually, I have a quote from NASA from a BA that they had. I don't know where they pulled this number from, but we've actually seen them in corpora of workflows that we've measured. We've measured workflows from different workflow systems, different domains, and they show this 60 to 80% of steps are really preparing data. So there's no reason why we can't share data preparation workflows that take data from, I don't know, NASA repositories that have satellite data about snow, and then share all these pre-processing workflows so that people can actually focus on running models and doing useful work. We're actually looking at reusing pieces of workflow, because sometimes someone has a whole workflow and you want to just reuse pieces. And we've been looking a lot at the pipelines and the workflows from our Loney friends on the third floor to see how much of the sub-workflows they reuse. And we've also done some work on quantifying the cost of having to redo those workflows from scratch. So this is an example of a workflow that we replicated, and it took us about 2 months. That's a typical amount of work that it takes when you read a scientific paper to replicate what was done in that paper. So this is a study in biology, and I've had others tell me that when they replicate work, it takes about that time. So this is a lot of time. If I could just take this workflow and reuse it, that would be a lot more efficient. Yeah, go ahead.
Do you consider something replicated when you were able to reproduce the experimental results, or when you were able to get basically data in what seemed like what they said without it crashing?
So that's a very good question, and it's a domain question. It's a question for the scientists. When do you consider this work replicated? So in this particular work, the scientists were convinced that the results were comparable. And the reason why they're not exactly the same is because the data sources that we were using, which were about drugs and proteins, change over time. And no one had a copy of the actual exact data source from 2 years earlier. So that's a big question, but it's kind of a domain matter, I guess. Okay, so if you have a lot of workflows, here I'm showing you workflows from population genomics, we can actually apply them to data that is out there and automatically get results. And here we were replicating results from papers and gotten the same exact results. So I think workflows are a very powerful way to let somebody say, I want to do a copy number variation detection, but I don't really know how to do that, and really reuse the methods that the experts would use. And because they're semantic workflows, they have a lot of knowledge about how to set parameters and what workflows are appropriate for what data. Another thing that we do with semantic workflows is exchange the workflows between different systems. So if we didn't have the semantics, it would be much harder. And what we do is describe the workflows with semantic metadata. So we say what data sets the workflows are using and what kind of data it is, from what location, from what sensor, from what time period, and so on and so forth. The workflows are published as web objects, and they're imported by diverse systems. So we can import them to browse them, to mine them, and so on. So this is very exciting work because it starts to make the workflows themselves open web objects. So here's two semantic challenges in this area. One is an automatic paper generator. So if you had access to all the biomedical data, all the genomics data, then you had workflows that capture common methods that are in the literature. So I see the genomics researcher saying, oh, you used an association test. I know what you did, right? So there must be something about that method that is commonly done. So can we just run these workflows in existing repositories, and as the repositories get more data or more information, maybe the workflows come up with new or different things. So maybe that will lead to a lot of new papers prompted by workflows. It's not a crazy idea. So there was a paper some years ago on automating science by David Waltz and Bruce Buchanan that pointed in this direction. Can we do automatic analysis of data and generate hypotheses and so on and so forth? So anyway, I think it's a nice, interesting challenge. And you need a lot of semantics to do this because it's not just running the steps. You really have to know how to calibrate them and how to check the data and so on. The second challenge is that I'd love to see a web of semantic workflows and processes. I'd love to see, oh, somebody did this method. I'd like to take it, just like I take a PDF of their paper. I'd like to take it and then play with it, rerun it. I would really like to have browsers that let me browse workflows. I would really like to have lots of software, just like you have a lot of spreadsheet management software. I would like to have lots of software that helps me run and look at and integrate and cut and paste pieces of workflows and processes. So that takes also a lot of understanding of when you mix things together, are they still valid or coherent? How do I find the right workflows? I would have to look based on semantic properties that they have, and so on. Okay, that's the second semantic challenge. And there's a lot of readings and pointers that you can look at if you're interested in this topic. Okay, so the third topic I wanted to talk about has more to do with collaborative tasks. And before I get to it, I want to get this question. Yes?
So if I have two workflows with the same input-output, how does one evaluate them, which workflow is better? Is it based on the accuracy of the final task or the time you saved? Or?
So when you say they have the same output, if you mean exactly precisely the same result,
You're doing the same prediction.
the same kind
From
of
same
type.
data sources and doing the same predictions. How do you evaluate two separate?
So it's a fantastic question. So when you put a scientist in front of several workflows and you give them a lot of choices, it's very hard for them to articulate. So, and we've done some work on this. So part of it is the quality of the answer versus the performance of the workflow. So in many cases, you can run the workflow much faster, but you're going to miss things out in your answer. So those are trade-offs that we don't find people have an easy answer for. And so typically they would want to see options. So they would want to see, here's a workflow that runs very fast, but typically has this much accuracy, and here's another one that will take you 3 weeks, but it has this accuracy. So we actually give them choices and options.
So you could potentially, if two separate groups have developed two separate workflows for doing the same task, you could actually just take subgraphs from one and another subgraph from the other and probably do better on the final task. One group might be doing processing better, the other group might be using better classifiers.
Exactly.
Get a better paper out.
Exactly. So we see, for example, I work with a group of climate researchers at JPL, and some of them use a set of Python code, another subset of that group uses Fortran, and another subset uses I forget, something different. And they can't use each other's things. So they say, you have better visualizations. I would understand my data better, but I don't know how to use them. You have better models, and you have better quality control. You clean the data better. So they can't really share any of that. So yeah, you're talking about this, super process, right? That really takes the best practices from each of the groups. Yeah. Okay, so let me talk about collaboration in science. This is something I'm very excited about in new work. So here's a workflow in the middle, one of the first workflows that we developed for simulating earthquakes. And what I notice is that it's not really that they have a workflow in mind. I don't know if when you do your work, you really have this particular process and this thing in mind. You actually design it as you go, and it's a collaboration that you do with others. In this case, they had people with different kinds of expertise contributing different pieces to the workflow, not just different steps, but opinions about the assumptions and the constraints and how it should all flow better together. So this is an example of the workflow from the ATLAS collaboration. So if you're familiar with the Large Hadron Collider and the work that they did, they had the ATLAS and the CMS collaborations. This is 4,000 people working together. This is their workflow. So you can see that they did a lot of work in parallel, but they had a lot of coordination points where they were actually putting things together. I don't know that they designed this beforehand. I think they were analyzing the data as they went, but this is what happened as the result of several years and 4,000 people participating in all of these activities. So I'm very interested in supporting these kinds of workflows of activities. If you look at scientific collaborations, they kind of mean different things. So I mean something very particular by collaboration, some very tight, very close collaboration. So you hear about scientific collaborations if they share instruments. For example, NEON has lots of sensors all over the Earth's surface in North America, and they're sharing all of the data from all of these sensors. Others are community data systems. So the Protein Data Bank is a collaboration tool because it helps scientists share data about proteins. Others are open community contribution systems. So Zooniverse, for example, is open. Anyone can contribute labels of galaxy pictures, and even high school kids go in there and contribute. Others are virtual communities of practice. So we are all interested in lakes, and so we get together and we try to collaborate as much as we can. Others are virtual learning communities. So Vivo is a project that has been set up to help people find expertise in other areas and get together to learn about best practices to manage scientific knowledge. Others are distributed research centers. So ENCODE is, and there's many others. It's a genomic project where many research centers work together to get these results. And other times they're community infrastructure projects. So all the people that build models of the Earth get together and they publish their models in the same framework. So all of these things mean scientific collaboration, but they're really very different from what I mean. So what I mean is, and I'll give you an example of the work that we're doing, is that there's many people with relevant expertise out there, but when I start the project, I don't know who needs to be sitting at the table. So I'm going to bring people in as the project progresses. People may have expertise, but also they may have data. So if I'm studying 20 lakes today because 20 people joined in and are helping, maybe tomorrow I'll have people that study other lakes, and I don't know who they are, and I don't know which of the hundreds of them will be interested in joining the project. So that's the kind of project I'm interested in. In this case, we're studying the age of water. So there's a lot of models about when a drop of rain falls in an ecosystem, how long does that drop stay and where does it stay? What locations does it stay longer at? So just trying to highlight that you don't know beforehand who might have studied different aspects of the age of water, whether it is data, water flow, or really what they call isotopic models. So we're starting small. So we're taking two communities, people that study catchments, which is hydrologists that study rivers, and people that study lakes. They never talk to each other. They both have looked a bit at the age of water, but they don't know what data each has, what models they each have, and so they're starting to negotiate and collaborate to integrate all of this knowledge that they have. So this new way to do science collaboration, we call it organic data science, and we're developing a framework to support it. So organic data science is shaped by three characteristics. One is that we want them to manage their tasks. We want them to share collaborative tasks and help them manage that coordination. The second one is that it really needs to attract contributors throughout the duration of the project, and they need to be motivated, but also it cannot be a high entry point to join the collaboration. And then we want to manage the participants so that they are really well appropriately incorporated, and we're looking at social sciences research to understand how to do that better. So it's really an open environment where the tasks and the collaboration are really exposed to everybody. And we call it an open task-centered socio-technical system. So it has those three characteristics, that it's open to everybody, that it's task-centered, and that it has this aspect of managing the social side of the system. So tasks, I don't have to say a lot about. These are some examples of how they plan to do lake models for a bunch of lakes. So they have a lot of ideas about what kind of data they need, and each of these tasks have different people associated with them because people have data from different places. In terms of opening science, I think what's exciting is that they see, for example, so I have pictures here from citizen science, but I won't get into it. But they have lake associations, for example, that wouldn't mind contributing data from their lakes, or if there's some task about cleaning all this data so that the temperature doesn't go over reasonable values, they'd be willing to do that if they could know what they were supposed to do. So they can also sign up for tasks. We take a lot of inspiration from the Polymath project. So it's built on a wiki, and math problems are posted publicly, and then people come in and then they decompose the problem into particular theorems or axioms, and then discuss them and so on. So this kind of approach to science, to really divide and formulate and divide tasks, is very successful in math. In terms of the social science aspects, there's a lot of studies about what keeps contributors coming. A lot of things on Wikipedia, a lot of things on open source software projects, Polymath I mentioned, and then also collaborative projects that are pretty large in genomics, for example. And what we have is a lot of social principles that work best. So there's a lot of simple things, but important things that you can do to keep the community going. So I'll show you some examples of how we do it. So, for example, when we have a task and we allow you to decompose it into subtasks and so on, one of the things that we have is that it has a start date and an end date. So even tasks that we plan to start next year are registered in the system, and so it gives you a heads up that there's a task that involves data from this lake, but we won't get to it until next March. So a social principle for online communities is that you should tell people when they should expect to get involved in a project. Other things include being able to sign up for tasks, decompose the tasks into reasonably small-sized tasks, so there's a lot of task decomposition going on here. And also, you can sign yourself up to be participating in a task if you just want to track it and contribute to it. As a contributor, every person, every participant in this collaboration actually has their own page. So there's where we help you track things that you've already completed, things that are ongoing, and we have a lot of icons to show you if you're late or if something doesn't look right or if someone is not doing what they're supposed to be doing. And of course, we have ways to describe data sets. We have a lot of structured properties about data that we can also support. The whole platform is built on semantic wikis that have a nice framework to be able to develop this software on top of. We also have models, so the software that they're using, kind of the workflow steps when they're implemented in software, and finally, actual workflows where they can combine different models together. Another important aspect in social communities is to be able to incorporate newcomers easily. So I'm showing you here what we've developed, which is a special site for training newcomers. And actually training to learn to use the site is formulated in terms of the same framework. So the tasks are train yourself in X, train yourself in Y. And as you complete the task, you can indicate that you've done them. And so you can see this user train themselves in all these tasks, and all of them are green, and they're all completed, right? So anybody can read the site, anyone in the world, but if you really want to contribute and sign up as a participant and do things, you have to go through some training. And if you really want to own tasks and formulate new tasks and add to that side of the wiki, then you have to be an owner, so you have to go through that training. So anyway, this is very quick, but just to give you an idea of how the site works. And we're evaluating what features in the user interface are most useful for people to find the tasks that they need to work on. So a lot of users like to see the subtask tree that is in the interface. We're looking at they're actually using the features that we're offering in the interface. This is just a heat map of the clicks that the users have, and they tend to focus on the features that we offer to navigate the tasks. Users are actually collaborating. It's the early stages of the project still, but and this is data for just the last couple of months, but 52% of the tasks are viewed by more than one person, 72% of the tasks have more than one person sign up for them, 19% of the tasks have more than one person editing, start date, end date, owner, participant. 11% of the tasks have actually more than one person contributing to the content. So the users are actually finding tasks as a nexus to collaborate. This is a picture of the social network. It's actually interesting because the sort of top half is the people working on the Age of Water, and the bottom half is those of us actually developing the software. So it's interesting that that's apparent. But there's actually a lot of links across everybody and everything based on the tasks that they share. Okay, so here's a couple of semantic challenges in this space. So one is I would love to see email-less coordination for projects. So in my dreams, I sign up to participate in a project and I don't have a stream of millions of emails and who said what 2 weeks ago and where was the pointer to this document. And it really helps me see the progress in each of the subtasks, what is late, who's involved in what, and I can go to a place where I can see what I'm supposed to do and what am I supposed to contribute to the collaboration. So this is, I think, a big semantic challenge to help describe these coordination mechanisms. Another thing is to really open science processes. So there's a lot of talk about open science data and opening science, opening PDFs, opening the publications in science. But I think I'm trying to emphasize the need to publish how we get things done. So it's not just workflows, but also these kind of meta workflows of coordinations and tasks that we do collaboratively with each other. And those would be very helpful to see. So I think this would be a fantastic thing to have. So I want to leave you with some closing thoughts. So Jill Tarter, who's the director of the SETI Institute, she looks for extraterrestrial intelligence. I don't know anyone who has more data and less resources to solve a problem. That's very clear. And she says we need bigger glasses and more hands in the water. So you have an ocean of water, as far as she's concerned, with her data, and you need bigger glasses and more hands in the water. So I like this quote, and I feel like that when I try to get work done. I just need bigger glasses, and I need more hands to see how things can get done through others. This whole idea of automating science and making science more efficient, we've been talking about discovery informatics. There's an article that just came out today, right? Today's the 10th. On amplifying scientific discovery with AI. I think it's very exciting to work on this topic. There's a big community working on this. There was a couple of workshops this year and one coming up in January, the Pacific Symposium on Biocomputing. So I think it's very exciting to pay attention to science. The scientists are actually paying attention to this. So this is representing the NSF EarthCube initiative to change the practices of geosciences. And they're talking about accelerating research. They're talking about knowledge management. And they're actually very interested in adding semantics and workflows and processes to what they share and what they consider science assets. This is a quote from Phil Bourne, who's at NIH. So this is he's the head of a biomedical initiative to transform practices in biomedical science in the US. So he talks about a vision where discovery informatics is in its infancy. He's imagining that you come back to the lab the next morning and there's some automated assistants that have been running overnight, and they're telling you stuff about your data and papers that you should care about and new results that they have found from running workflows for you. So I think the scientists really can see that they need new kinds of glasses to browse through the oceans of water that they have. So I told you about a bunch of semantic challenges in getting work done. So managing personal to-dos, managing in coordination your to-dos, and then a number of semantic challenges in science. So doing an automatic paper generator, a web of workflows and processes that we can only use. And then I talked about opening science. So what if we had email-less coordination of projects, and what if we had a complete open science, including processes? So I think these are all very ambitious challenges where semantics has a big role to play. And I'll tell you, what will the future look like? So I run into people at conferences and meetings all the time, and I say, what are you working on? And they'll tell me, oh, I work with time series data, blah, 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 or I work in social network analysis, or I work in geospatial data. Everybody works on data. I want people to work in processes, and I just hope that, a few years from now, when I talk to those people, I can respond and say, yeah, but aren't you glad that we can get our work done faster now, right? So that's all I wanted to say. Thank you. Questions to the magic microphones? Kathy.
So there's a guy who writes a lot of books called Getting Things Done.
Uh-huh.
And one of the things that I tried to apply this to my life and find it difficult, but it's kind of ongoing struggles, and I'm sure it's most people. One of the things he identifies as the kind of key thing that he thinks is his whole approach is to segregate the different contexts of tasks. So when you're out shopping, he wants a tailored shopping list for that context, just that content. And so it strikes me that a very general question, a kind of low-level semantic question that is inherent in everything, in all the stuff that you were talking about, but primarily the first part of it, is the study of the semantics of the context of tasks.
Yeah.
Do you have a theoretical or a kind of a model view of that any way of breaking that down?
So Jerry is not here, but I think that's exactly the kind of research that Jerry Hobbs does. So how do you understand the tasks, the processes, the different contexts that you have in the world, and how do you situate new information in that context, right? So people are extremely multidimensional. So even when I talked about this data that we collected from to-dos, from people in an office environment, they knew they were being monitored, their to-dos were being captured, but I can tell you that more than half of the to-dos at least were things out of the office. So things to do with, don't forget this, don't forget that, don't forget this, don't forget that, pick up milk or whatever it is, mom's birthday. So you're right that we have all these different dimensions to ourselves, but in some sense they're intermingled in other ways. So anyway, it's a great area. So this personalized information space and representing that would be a fantastic thing, yeah. Go ahead.
I have a question about workflows. So you described very nicely a lot of the benefits of workflows and semantic workflows. But some of those benefits come for a cost. And so just, from very low level, this was a very nice high-level overview from very low-level personal experience, often producing a workflow that just glues together a whole bunch of processes. Just writing a script that in the end does everything is a very difficult process. And so getting this up one level higher, where you're not just gluing things together, but you're actually describing all the dependencies, all what these things mean, how they interact, to me appears that there's a certain cost involved there. So what's your experience? How do you quantify that?
So there's a cost to that, certainly. So if you develop all of those codes and scripts for yourself, or you work with someone who understands all of those codes in your scripts, you don't need to build a workflow. There's no need. You're just causing yourself overhead. But the kinds of situations where it's beneficial is when you really want to convey the expertise that you have in running those codes. So I cannot tell you how many times I see the scientists running code with data and saying something's wrong because that curve doesn't seem right. And so they'll look back and they'll say, let me see what that step is, output is, and they look. And then they change something and then everything looks okay. So that knowledge about what things should look like and what was wrong with how I set this parameter, that's the kind of knowledge that I want to capture, because the next person doesn't have that kind of knowledge. So, and I'll give you one of the problems we're working on. So I have clinicians in Children's Hospital that work with data mining researchers. The data mining researchers write all those codes. And then they show the clinicians pictures of, here's a cluster of your patients, here's another cluster, do these make sense? The clinician would say, not so much, because I would expect this and this. So machine learning people go back and change some parameters, come back, and so on. So they do these negotiations. But the clinician cannot experiment with this instrument, which is the data mining software. So my vision is that instrument should be available to the clinician to run it and to say, oh, what if we had more clusters? What if I change the density of this? What if, I don't know what the nucleus blah, blah, blah seed is, but that's a parameter I can change. I'll set it to this, and the system's saying, sorry, if you need more than 10 clusters, you shouldn't be setting this so low. I recommend this value. So you work through that, and then you can see that the clusters of patients and until it looks right to you as a domain expert. So really this business of transmitting the expertise requires work in describing these algorithms and so on, but it has these benefits of having that expertise out. And as I said, there's not enough data mining experts to go around. So I think if we're going to scale that expertise to all the kinds of data and all the kinds of problems and all the kinds of science research, you have to find a way to capture it and disseminate it electronically.
So, this is interesting because my experience is that the semantic systems are so neat. They want you to input all kinds of stuff before they can start to help you. And then the rewards are way down the line. And so I think that poses an enormous challenge. You see that we're making progress in doing more pay-as-you-go kind of semantic systems that don't require so much neediness.
Mm-hmm. Yes. So in our case, for example, our semantic workflows, since you brought that up particularly, our semantic workflows don't know everything about the algorithms that they're running, right? Representing that would be an enormous amount of work. So there's, deep statistical techniques, or, go describe how an SVM works, or a system of differential equations. We don't describe that. We just say enough that you can run that software with the data at hand. And that's a different kind of knowledge, right? It's a more shallow knowledge. It's a more practical knowledge, right? So I don't need to know what an SVM is. I need to classify these documents, and I know that's what people use, and it may have these parameters. Just help me set them up so that my documents are classified as I expected, right? So I think we really are, doing this incremental semantics. So some of our workflows simply have ways to set parameter values, and others have more sophisticated descriptions of the data sets, and so it depends on what kind of assistance or reasoning we want the workflow system to do. So it's very amenable to doing this piecemeal semantics.
The first part of the talk, you looked at the to-do list, and you said we did lots of research, but this is a tough problem.
It's too hard.
It's too hard. We could not do even the individual to-do list, forget about coordinating to-do list between multiple people. But then in the third part of the talk, you said, I'm going to build down organic science, data science, place where the critical thing is to coordinate work by providing a task-oriented nexus or whatever, which is more or less to-do lists between multiple people. So why do you think you have a chance to succeed if the first one was too hard and you have 10 years of experience there?
So there's a difference between the first one and the third one. And in my work, I've always navigated this, this ridge between formal representations and semi-structured representations. So in the case of the to-do lists, I really wanted to understand what the to-do was and get agents involved and be able to find methods that were appropriate or websites and methods that I wanted to understand the to-do. Okay, so I was leaning more towards representing and understanding that to-do. In the organic data science case, there's nothing in the system that understands the nature of those tasks. The system does not understand that you're actually, normalizing data for the lake metabolism, blah, blah, blah. It doesn't understand that. So I'm more in the semi-structured area. What we are structuring are silly things like the start dates, the participants, the deadlines for that task. So the other tasks that it's related to. So it's creating this very shallow semantic model of the coordination aspects of those tasks. That's the difference between the two.
Okay, thank you, Rhoda. So let's thank our speaker.
Thank you. Sorry?
Head of G-Bucks.